Hello and welcome again for another hardwear.io webinar. Friends, we run one of the only hardware security conference in the Netherlands and USA called hardwear.io. We have some really cool hands-on live hardware trainings coming up for you in the month of September. If you're interested, please do check our website for more information. My name is Antriksh and I would be your host for the day. Well, we all have seen various news articles and stories about car hacking and how someone can take control over your vehicle over the internet. Vehicles use a protocol called CAN bus to communicate between devices and its microcontrollers. CAN is not only used in automotive and railway systems, but also in healthcare, elevators, industrial automation devices. CAN is a very old protocol being used since 1980s, and there have been multiple ways where researchers have found how to sniff and stiff the communication and cause issues in the systems using it. Let's invite Dr. Ken from Canis Automotive Labs on how we can directly address the security of CAN, like anti-spoofing and protection against denial of service attacks. Dr. Ken developed the Deadline Monotonic Analysis for the CAN bus and also an automotive real-time operating system called LiveDevices, which was later acquired by Bosch. So let's welcome Dr. Ken to deliver his presentation.
Hi. Nice to see everybody.
Ken, do you want to start sharing your screen?
Yeah, so I'll just share my screen.
All right. One quick information, friends, if you have any questions, please type it in the Zoom chat. Dr. Ken would answer them after his presentation is complete. Over to you, Ken.
Okay, so I'm going to talk here about very briefly about some of the CAN security issues, and then talking about how to secure CAN bus against those attacks by augmenting the CAN protocol itself with additional hardware. So just a quick intro to CAN. It's a really useful networking protocol. It's got really important properties for embedded systems. So for example, the message, even though the bandwidth is low, it has very short message latencies. It's atomic broadcast, so that when a message has been sent, everybody on the bus has got that message and no one's missed it. So it's really well designed, but it's pretty old. And we see today Ethernet's got 100 times the bandwidth, but Ethernet struggles to replicate those facilities of CAN. So even though CAN is old, 30 years and more, it's going to be with us for many years to come, I think. But the big problem, because it's so old, is it doesn't have any security, because it was conceived in the 1980s before there were connected cars or an internet for them to connect to. So it didn't cross anyone's mind that security would be an issue. But we now need to address this for CAN, because CAN is where all the vital actuators are controlled. You can detonate airbags via CAN messages. You can open doors. You can screw up all kinds of mechanical things by getting control of the CAN bus. So how do people get control of the CAN bus? One is physical wiring. You find a part of the system where the bus has been exposed, so criminals know that under a particular wheel arch, maybe there's sensors for some kind of steering system or ABS, and you find the wires and you cut them and splice in a device directly onto the bus. Or you might just use an OBD2 dongle that you've plugged in. Lots of third-party tracker and immobilizers use these dongles for providing their services. So if you hack their services, you can hack onto the CAN bus through their devices. And some people are even putting emissions cheat devices in. You can buy boxes that pretend that there's plenty of AdBlue system in your truck, and in fact you're just spewing nasty emissions everywhere, and you're using that to cut the cost of AdBlue by cheating the emission system. So basically you can get on by physically attacking the vehicle, or you can hijack an existing device connected. So if you can exploit a vulnerability in a piece of ECU software, you can push malware in, take over that device, and now you've got access to CAN through that device. So car infotainment, for example, is a classic. These are the ones we always see. people are hacking car infotainment because it's big bloated pieces of software that are not kept up to date. But things like insurance companies now push out dongles to customers to plug into OBD2, and then the insurance company is talking to its own dongle and listening to CAN frames. So the entire chain now, from the app to the insurance company's back-end systems, all the way through, if that's hacked at a particular place, you could get access to CAN bus that way. We've seen actually proof of concepts of hacking a telematics unit was done back almost 10 years ago by Stephen Checkaway's group, where they used a telematics and an actual dial-up modem, radio modem in those days, and were able to get access to CAN. So it's been a problem for a while now. But it's not just big systems like infotainment, also little tiny embedded firmware systems. So, for example, we've seen tire pressure monitoring systems have been crashed by fuzzing the sensors, the radio sensors from the tires. You can just step in and pretend that. And of course, once you can cause a system to crash, that's normally an indication the stack has got screwed up in some way, or there's a buffer overflow, and that's the first step to a remote execution vulnerability. And then we've seen libraries. So if you've got a diagnostics over IP and you're using that Track TCP/IP suite, huge remote execution vulnerabilities have been discovered in that recently. Now, there are a couple of types of attack. I've tried to categorize this here with CAN. One is frame attacks, which you make via a CAN controller. So the frames sent on the bus comply with the CAN protocol because they're coming out of a CAN controller. So an OBD2 dongle connected via, say, Bluetooth to a laptop. The dongle itself has got a CAN controller on it, and it's the hacking is via, say, the laptop. So it's just frames. And a hacked infotainment system, and you use the Linux socket CAN API, you're sending out CAN frames. The other approach is with protocol attacks, and that's where you hijack the CAN transmit pin on the CAN transceiver, and then you don't have to follow the CAN rules. You can send any pattern on the bus, and you can craft special attacks that exploit features of the CAN protocol. So you wouldn't be able to get access to these if you sent them as frames from a CAN controller, but if you can take control of that pin, you can do all kinds of things. And I wrote a library, the CAN hack library. It's I've got a link on here. You can play with it in GitHub, just to prove the kind of things you can do just by taking control of that pin and bit banging CAN protocol. So on frame attack side, the number one attack on CAN is, and this is what everyone is showing, is a frame spoofing attack. And that's really easy to do with the CAN controller. It's what I call an authentication attack. You get the receivers to accept the CAN frame as legitimate. But that's pretty easy to do. You just push a CAN frame on the bus, and when the receiver sees it, they just assume it's come from the right place. Another example is a bus flood attack. So you send frames that aren't spoofs, they are coming from the right place, but they're more often than allowed. So maybe you'd send something through infotainment that's allowed to come out, but you flood the bus. So maybe the infotainment is lighting up a light on the dash when something happens, and you flood the bus with frames of that, and all the frames with lower priority basically get jammed off the bus, and they exceed all their latencies, and then that causes timeouts and stuff. And the timeouts and lost frames are occurring in different ECUs than, say, the infotainment. So it's actually quite hard to work out where the attack came from. And that's a denial of service attack. So on the protocol attacks, it's just very simple here. You reconfigure the IO port. If you've got an on-chip microcontroller with an on-chip CAN controller on it, you just you tell the microcontroller to turn that CAN TX pin on your microcontroller into a GPIO pin, and then bit bang software to drive that pin. And once you've got control of that pin, that is complete control of the bus. I mean, you could just send a 0 to that pin, and that would lock everyone off the bus and permanently kill the bus. That's the easiest denial of service attack when you handle bit banging. So here is just a link if you want to have a look. I've got a little website and a description of that, and there's a YouTube video showing a bunch of those attacks and how they can take place. They can do all kinds of things. I won't go into details because there's not time, but there's a big YouTube video there showing them all actually happening for real. So those are the kind of attacks we see on CAN: frame and protocol attacks, denial of service, and authentication. So how do we mitigate that? Well, the normal approach is you start to take all your infosec stuff from the main iStream IT world, and you have, let's have a intrusion detection system. So you basically have a look at traffic patterns on the bus and see if there's something a bit odd about it. So if an extra frame comes in more often than expected, it might be a spoof because it might have come from an attacker. But there's a problem that there are false positive and negative. So you spot some extra frames have come through, which you're pretty sure are spoof frames, but you don't know which ones are the spoof and which ones are the real ones. And any decision you make, the malware could merely make sure its frame came before or after where you thought it was and break your algorithm. So you can detect that there's some kind of weird thing going on, but you can't actually stop it. Now maybe that's okay for certain applications, but it's not okay for others if you're worried about the actuators being controlled from CAN. So the second level of mitigation is a security gateway. So you put all the high-risk devices behind the gateway, and then you firewall it to the main bus. So you don't send through frames except the ones on a list, and you don't send frames back unless there's a need to know them. So OBD2 ports should be behind a firewall so that they can't see the CAN bus directly, and then you can't sniff it directly. But there's a ton of problems with this. One is that it doesn't actually stop you hijacking a device if you can do that via legitimate traffic. So if you can send a diagnostic set of diagnostic commands and they cause a Stack Overflow bug or something, they can go through OBD2 because it's supposed to pass through diagnostic commands. And there's a bunch of implementation issues. Again, get in touch with me if you want to talk about priority inversion in frame queuing. I've got a little video explaining how that problem is. And then there's problems of securely updating the firmware, securely programming the filtering rules. Itself, the security gateway could be vulnerable with its own security issues. And then there's encryption that everyone proposes. And if you have a crypto hammer, every security problem is a nail. You will apply crypto, and hammer every problem with cryptography. But it's not actually that great a solution in the end. So it provides authentication. You add an authentication code to every message to prove that it came from not the infotainment, but the engine management system. But there's a ton of issues with this. And I know this because I built a crypto system for CAN. So first of all, it doesn't address denial of service attacks at all, or CAN protocol attacks, because it's above the layer of the CAN protocol. There's all kinds of issues with key management because you need secure key distribution, and then you need to make sure you can't roll them back, and all kinds of stuff like that. That's a whole lot of problems. And there's implementation problems. There's high CPU overheads. There's you've doubled all the bandwidth if you want to put 64-bit keys on every CAN frame. There's an issue with how you synchronize devices into a system. Most crypto systems have like key exchange, but if you've gone through a watchdog reset, you've now lost a whole bunch of your session keys, for example, and they've got to bring them back on, and you can't talk securely until you can get back in. So that's a big problem. Replay attacks is a problem. If you replay a message that's got an authenticated code with it, so you just store a copy of "please unlock the doors" and then replay that later on when you want the doors to be unlocked when the owner has gone away. So fixing that brings a whole lot of problems. And then the worst of them is there's actually no deniability for a lot of these encryption systems because they're symmetric with shared keys. If you hijack a node that's got the shared key that everyone is using to authenticate all their messages, then you can generate legitimate messages that appear to come from somebody else because you've got the same key that's being used to authenticate that. So you can still spoof frames. So you've gone around all of this stuff, and in the end, encryption has bought you almost nothing in terms of protection from authentication, denial of service, and all the things we've been talking about. So we should take a step back. What do we actually need from CAN security? Firstly, we must authenticate CAN frames so that only frames from the legitimate sender get delivered to the receivers. That's a pretty simple requirement. And we must have denial of service protection. So you shouldn't be able to flood the bus. You shouldn't be able to even flood in a small dampening or a little rain shower just as a frame is supposed to be turning up. If you just flood for a little bit, you could cause that frame to miss a deadline. And if it misses a deadline, it causes a timeout, which causes a fault system to be triggered, you shouldn't even be able to flood for a little bit of the bus. So we need complete protection of the CAN bus, because it's got to be able to operate in all circumstances and resist the attacks. And we want it to work, any security system, we want it to work with existing CAN networks. Obviously, we don't want to have to rewire an entire architecture and change everything just for trying to secure it. And ideally, we wouldn't need anyone to change any software, because changing software when you've got tons and tons and tons of reusable components with fixed APIs is a real nightmare. So the solution is that we use hardware, but hardware at the CAN protocol level, and to do these things in hardware. And let's see if we can step out of the way of the software. So the first guys to address this that I've seen is NXP. They've got a secure CAN transceiver, and inside the CAN transceiver itself, they've got a list of frames that are allowed to go and a list of frames that aren't allowed to be seen. And what happens is, if you, for example, if you send a frame from a host and the ID is not on the outgoing allow list, then that's an attempt to spoof, because you've got all the list of frame IDs you're allowed to send, and you're sending one that's not on the list. That's a spoof. So the transceiver actually steps in and destroys the CAN frame with an error, and then it doesn't get through. And any frame that you see on the bus that has an ID that matches one on your list, then somebody else is trying to spoof one of your host's frames. And so that is also a spoof and destroyed. So that list, if you like, is the security logic for outgoing frames and incoming frames, which is okay. And then there's a kind of anti-denial of service attack feature where they have a leaky bucket algorithm to limit the rate that frames go out, so they can't be completely flooded. There's a couple of issues that have to be solved for this kind of technique to work, one of which is the programming of those ID lists. That has to be secure. Because if you physically can't get to a box, once you've installed an ECU deep inside a vehicle, you can't get to it to take it out, put it on the bench and reprogram it. So that has to be programmable over the CAN bus. And it has to be an atomic system with some kind of transaction so that the same lists are consistently applied everywhere. And it has to be a secure method to authenticate the messages doing the programming of the lists, because otherwise malware could just rewrite the lists. So now you are bringing back all this requirement for, in order for this authentication system to work, it has to have an authentication system. This is interesting. And then the leaky bucket algorithm is actually weak protection against denial of service. Bus flood is a crude attack, but you can get a subtle bus flood attack, which just causes 4 or 5 frames, for example, in just the wrong place, to cause a targeted frame latency to be exceeded. Then it triggers a timeout, and then you've got your timeout response that you may be needing elsewhere. And we've also got to protect against CAN protocol attacks, and it's not really clear which ones of these. The bus off attack is a famous one, but there's lots of other attacks. The Canis attack is one I came up with, where you can actually have multiple payloads inside a single CAN frame, and different devices see different payloads. So you can see that on my CanHack website. So let's come to CanHG, which is what my company's working on. It's basically we augment standard CAN, and the HG is for higher speed with security features to guard the bus. And what we do is we put out-of-band data inside a CAN frame, and that data is invisible to CAN controllers. So therefore, it's fully compatible with CAN. It's still CAN. They're CAN frames. Devices that don't have the hardware don't see any of the out-of-band data. So you can use existing CAN controllers. You can use all the same wiring topology, and you can fully mix CAN and CanHG on the same bus, because it is CAN. And the way we do it was, this is a CAN frame. Here's a couple of CAN bits. So at 500 kilobits, that's 2,000 nanoseconds long. And with CAN, there's you have the bit time is allowed for sort of propagation delays and so on, and there for the way it does arbitration. And then there's a window in which all the devices have to take their samples of the CAN bit. But after arbitration, that window is unnecessary. So what you can do is you can inject extra high-speed little bits in the gaps between the sample points under certain conditions. And those bits run a lot faster. These are 104 nanoseconds. We can make them go slower if necessary. And that's 10 megabits. And we call those fast bits because they go fast. So that's how we encode the data. And then the basic concept for the security is the out-of-band data encodes a hardware source address of where the CAN frame came from. So as the CAN frame goes out, we find a place to inject this CAN HG header, which contains the source address, and that basically tags in hardware where the CAN frame is coming from. And there's no software required to drive that. There's no configuration required. You just need to burn in or on a PCB define the hardware address of the device. And then a centralized intrusion detection, intrusion prevention, or IDPS, has hardware to take that source address out, decode the out-of-band data as the CAN frame is received, and then use the CAN ID and the expected source address, check where it came from, what it's sending, and then you can decide if that's a spoof frame or not. And that's crucially, that's all happens before the frame is finished. So the IDPS software gets an interrupt from the hardware module with the information, tells the CAN hardware, the CAN HD hardware to generate an error frame, and then that destroys the frame. And that provides authentication. So if a frame has been received, it was never destroyed, and if it was never destroyed, then the IDPS let it go through. So there's no need for the software on the host to do anything. So here is how you would do what we call the Guardian hardware. So that sends normal CAN bits out, and then as they go through the system, they get augmented with extra fast bits injected in that come basically from the source address through the hardware. And then that's what goes out through the transceiver onto the CAN bus. And then the other end of this is there's an IDPS somewhere in the system, and this gets out-of-band data back out again from the CAN frame. So that gets the data, but it also gets events. So like now we have the CAN ID, here is the header, and this happens before the end of the CAN frame. And then this system can tell this, if it decides the frame is not allowed in this context, to destroy it. So this is how it kind of works. So you have an ID, a body, and an EOF of a CAN frame. So the ID goes out, and then we get an event at the IDPS that says, here's the ID. Then as the body, the payload, and DLC fields and so on go through, it gets tagged with the header, which is an event generated. And then the IDPS has time to make a decision and then can decide to kill the CAN frame. So it pushes an error frame on the CAN bus, and the CAN protocol destroys that frame, and then the system recovers as normal. Now, destroying that spoof frame is only the first layer of protection. So it stops anyone receiving a spoof frame. But the sending CAN controller will just retransmit that frame, typically, if it's coming from a CAN controller, because the CAN protocol requires a retransmission. In fact, you want that because that's what gives atomic broadcast. And then the IDPS will destroy the frame again. And so that'll go around in a loop and a loop and a loop until the sending CAN controller goes bus off. And if the sending CAN controller's idea was to destroy the bus traffic, it would just reset the CAN controller and try again and carry on. And the bus is now full up with all these error frames. So without denial of service attack prevention, that spoof attack just becomes transformed into a denial of service attack. In effect, we're doing like a bus off attack ourselves against the attacker. So that's no good. So in the Guardian hardware, there's also denial of service protection. So the way that works is the IDPS can send commands on CAN with an ID of 0, and then the bus Guardian hardware listens to these special commands and then acts on them. And there's a whole bunch of commands, but one of them is to tell the bus Guardian hardware to disconnect the host. And then the disconnected host can't now retransmit because it's been taken off that. So this stops this doom loop of retransmissions. And the IDPS can later send a command to readmit the host back in again. All kinds of options. The whole idea is to be flexible here. and the Bus Guardian hardware disconnects the host using CAN overload frames. That's a legacy feature of CAN. Overload frames were invented in the 80s, early part of the protocol because back in the 80s, the hardware couldn't keep up with the full speed of CAN protocol. So it had a kind of X on, X off flow control kind of feature, and an overload frame. They never generate anymore because all the silicon's fast enough. But we use that and basically use that to freeze the host's CAN controller. So instead of sending it bus off, it doesn't know that it's been disconnected. It's just everything appears to be going really, really, really slow. So if the host had reset itself in some way, it's a transient attack, then you can bring it back online without needing to get it to recover from bus off. So I can demonstrate this now with a little demo system. It's basically some of our, we use MicroPython boards in our lab with Python firmware, MicroPython firmware, and then we interface that to the embedded software because it's a really nice framework for running up tests and scripts in Python. So we have a CAN bus adapter. We have a microcontroller board I just showed here. Then there's an FPGA rig that connects that through to the CAN transceivers in these rack cards that we've got for doing experiments. And then we just use a logic analyzer to see the whole thing. So here's the logical structure here. We have centralized intrusion protection system with our CAN hardware in it. We have a node here, which has also got a Bus Guardian, and it's going to be a spoofing attack node. And then we have another node here that doesn't have any special hardware, and it doesn't have a source address. So we're going to attack from a guarded system and attack a frame that would normally come from, and try to spoof a frame that would normally come from B. So these three here are our terminal windows onto 3 different microcontroller boards. So the IDPS is here with address 1, and then A has got address 2, and then B, we don't have an address. So in our little Python framework, we make it easy to type at the command line and set this up. So we bind a CAN ID of 123 to address 2. And then we bind 124 to no header, saying that it doesn't come from anything with the CAN HT header. So we can just send some frames from that and just check that it works. So there we go, frame 123 with our cafe food payload comes out in our CAN bus analyzer tool. 123 cafe food. So that's all working fine. And then we have 124 with our famous dead beef. And here we are, 124 and dead beef. So let's try spoofing now. So here we are at A. And we're going to create a spoof frame, which is ID 124 to do the spoof, and it has fibbed as the payload. So if we get the logic analyzer going, we can see what happens when we send it. So arm the logic analyzer. And we send the frame spoof. Okay, so it's a little tiny glitch, what looks like there. In fact, if we zoom in, we'll find that's a whole CAN frame. So zoom in. Okay, so here, this is the CAN HG header with our fast bits. So these are the slow CAN bits you can see here. And then that's the header. So that comes through, and the IDPS has been told about it here. It knows it's got the header, and then by here, it's made a decision to inject an error frame and kill it, because ID 124 shouldn't come from a device that even has a header, let alone the wrong address. So that's the error frame, which is 6 bits. Zeros, 6 dominant bits, and then 6 recessive bits. So that's the error flag. and that's the error delimiter, and that's the standard CAN protocol. So here is where we finished, and now we are sending a new CAN frame, and that's CAN ID 0. That's come from the IDPS, and we can tell because it's got its own header, the source address on it. And then this payload here is basically a coded instruction to tell the Guardian device to turn off. And so you can see that here are the two frames that went through legitimately. Here is the error frame that we just saw. Here is the please shut up and tell your host to disconnect. And then that's it. There are none of these. We would expect normally with CAN a repeat of this in a loop for 32 times before it went bus off. But none of that has happened here. So we've shut the device down, and that's stopped the denial of service attack. So I think it's important to take a perspective of what's going on here. There's no security policy in the Bus Guardian hardware, so there's no lists of frames, there's no ID lists, there's no configuration other than just the hardware address source address tag, and all of the logic and policy is all done in the central IDPS, and that's all done in software. So the software is deciding what to do, and then is using the mechanisms in hardware. Because if we try to put policy into hardware, we're bound to get the wrong policy for somebody's application. So it's using a bunch of mechanisms. One of the mechanisms we have in the Bus Guardian is a security error counter. So if it detects some of these protocol attacks I talked about, like a spurious error frame, that's part of the bus off attack, or if we're glitching CAN bits, for example, that's how the Janus attack works. Those are detected, and then an error counter is implemented, and the detection of those also results in an error frame to make sure that the bus has been cleaned of the attack. And then there are other protections like address protection. So if the Bus Guardian hardware detects its own source address being used by another CAN frame, that could be a forged CAN frame with a CAN HD header. So someone connects up their own piece of hardware to the bus and they inject a fake header. They still can't spoof the device because the device being spoofed will see its own source address being used. So the Bus Guardian hardware has some logic for security mechanisms, but they aren't part of security policies of how that would work. So in terms of how you would deploy this, you need at least one IDPS on a CAN bus, and then CAN Guardian hardware in all the ECUs that you have security issues with. So you don't need to deploy the Guardian hardware everywhere. It depends on risk assessment. So you would put it on ECUs that are most at risk of being hijacked and being the attacker. So you can identify where the attack frames are coming from, or you put them on the ones most at risk of being spoofed. So in the example, we showed the formal where ECU A had the hardware and B didn't. But you might, if you wanted to make sure, for example, locking or security commands for door locks and stuff, you might put them on that, not because they're at risk of being hijacked, but because they're at risk of someone hijacking their frames, and therefore you want to prove it didn't come from there. And then the high volume deployment of this, basically the Guardian hardware has been designed to have the absolute minimum number of gates and be integrated into a CAN transceiver. And the reason we can put it in a CAN transceiver so easily is that the gate count is small, but there's also no requirement for non-volatile memory. So we don't need flash, we don't need EEPROM. So it means that the silicon process for power electronics for CAN transceivers is compatible with the logic gates that we use. And then the IDPS, that could be on a standalone device, a centralized IDPS. One of the common deployments of this is the IDPS sits on multiple buses. So there's kind of, it monitors 4 or 5 CAN buses, and it's also the gateway between the CAN buses and stuff. So there's maybe an ECU that's a centralized gateway could be the place to put this. Or it could be integrated into an application SoC. So if you're actually doing a custom SoC for an ECU, you could throw some more gates in there and put a parallel IDPS module into the SoC that runs independently of the application processor, depending on where that ECU is going to be wired up. And we have a partnership with Ultrasoc, where we are working with them to put the Canis IDPS hardware inside their wider security solutions. They've got a whole load of security sentinel stuff for monitoring things like the Axibus to see if the host software is misbehaving, but also for monitoring the CAN bus and talking over CAN to those sentinels. Low volume deployments, we can go to market with FPGAs. Because it's a tiny number of gates, the Bus Guardian will actually fit into these literally tiny 3 square millimeters from 3 FPGAs. So you can run that down on most ECU hardware. And then the IDPS can run on an FPGA with an integrated Cortex M3. So that's what we're working on at the moment, is a standalone FPGA IDPS. And we have IDPS software. Obviously, that's not necessary for the concept to have our software, but it provides authentication and denial of service attack protections. So it has global settings for things like do you want to ban all remote frames, or unknown frames are allowed or not allowed, and it's got the allow deny lists for each ECU, but it also has modes. So in different modes, different frames may be legal or not legal. So for example, OTA, over-the-air firmware download frames may be legal only if you're doing over-the-air download, and outside of that, anyone sending over-the-air frames is a hack. So in the when the IDPS knows about the over-the-air mode, it switches and says these things shouldn't be seen and these things should. And then when you're in an operating mode or in the vehicle station, the vehicle's moving, all kinds of logic you can apply here. And this is what I mean by this policy: is the policies are very, very specific to any particular OEM or any particular vehicle platform, and you don't want to put that in the hardware. So that's why this is in software. It also provides real-time protections for bus flooding. So not just the simple dumb bus flood attacks, the really well-crafted ones that send frames just at the wrong time. This can detect those frames being outside of a time fence, effectively. So we've got a real-time budgeting of where frames should occur, and then the system can be shut down if it exceeds that. That's also useful in the case where you have what the fault-tolerant guys call a babbling idiot problem. So you've got a bit of software that's just gone crazy. It's not an attack. It's just gone crazy. You can stop it taking down your CAN bus, and that's an essential property you need for high integrity systems, is to shut down crazy nodes that otherwise would disrupt the bus. So the status today, we have standalone FPGA solutions right now. We're finalizing the draft CAN HG specification, so we're forming a special interest group to formalize that specification, so that we can have different parallel implementations in hardware from different people. And we're currently working on a specific version of our IDPS software for J1939, because that's, if you like, a parallel to automotive market of highly sensitive vehicles that are frequently connected. And J1939 has got specific addressing systems in the CAN frame itself, so we can cross-check much easier the address in the CAN frame ID with the address of the hardware out of band data. And we are undergoing hardware IP formal verification right now. So all of the modules are formally specified and going through a formal proof verification. So to summarize, we looked at the types of CAN bus, frame protocol, authentication, denial of service, and we looked at all the different mitigations. And I've told you about the CAN HG one in quite a bit of detail. So we provide authentication and denial of service protection in hardware while remaining completely compatible with CAN, because it is CAN. Just one last thing. I know we're a bit late on time. I'm sorry for that. Those fast bits encode the 8-bit source address in the CAN header and the CRC and stuff like that, and they're set for every outgoing frame. But it also contains an HD body flag in that header, and that says there are more high-speed bits to follow to form a body. And a body is got things like a 32-bit timestamp, which tells you the clock, free running clock of the sender, With that, with your free running clock, when you receive it from the starter frame pulse, you can work out global clock distribution accurate to a microsecond. And we've got a high quality 32-bit CLC there, which also resolves a problem with CAN's CLC calculations. And if you put an 8-byte frame through with a whole payload of zeros, you can carry 100 bytes of user payload data inside those fast bits. So CAN isn't just secured by CAN-HG, it has 12 times more bandwidth if you use CAN-HG to carry extra data, maybe between a couple of nodes only. So if you want not just a secure CAN bus, but you're running out of bandwidth and you want it to go faster without having to rewire everything, restructure everything, give us a call because we can make it run faster. And that's where you can give us a call.
Thank you, Ken. I've received a few questions. Let's see, based on the time, how many could we answer? Okay. Let me ask you the first question. This seems like the CAN Plus protocol proposed by the folks from Leuven. However, that never gained commercial success. What is the difference here?
I've not heard of that.
All right.
Drop us an email and tell us about it.
All right. I have received another one. Will the IDPS software be fast enough to null out the shortest possible frame needed for DOS?
Yes. So actually, CAN frames are very slow. There's 2 microseconds per bit. So you've got loads and loads and loads of time to decide. And okay, loads of time is a relative thing, but if you've got, say, 10 or 15 microseconds to make the decision on a reasonable microcontroller that's at least not weighed down with loads of other software that's going to disable interrupts and stuff, is you could do that on an 8-bit microcontroller. The key there is not to try and do this on a Raspberry Pi or something where it's busy and locking out interrupts for long periods of time. But there is lots of time.
All right. There's another question, Ken. Are hardware IDs going to be programmable?
Yeah, so the idea here is that there's lots of ways that the hardware IP block could be programmed in. One is you could use DIP switches on a PCB, but that's not very good for high volume. So the idea here is, although you don't need non-volatile, you can't do non-volatile memory in power electronics, you can do fuses. So the idea here was they would be set at factory time by blowing fuses, and the configuration of the system is set up with those 8 bits at factory time, and the fuses means that they can't be destroyed or changed. So the software is unable to ever change the source address, and the source address is a physical location within a design. So there's no need to change the address.
All right. Is there any question from anybody else? Please use the Zoom chat. Well, Ken, there aren't any more questions. So yeah, thank you so much, Ken. It was a wonderful presentation. We will, for the audience, we will also have this available on our YouTube channel. So, if you want to refer it to somebody else, please do. We also request you to send in your valuable feedback. We'll send you the feedback link over Zoom chat and also after this webinar. Until then, next time, stay safe.
Thanks.